We went to the moon more than 50 years ago, so why are we still not on Mars? Because Mars is not just farther away, it changes the entire mission. The moon proved we could reach another world, but Mars asks a much harder question. Can humans survive the trip? Land safely, live there, and still come home? But before we continue, please subscribe to the channel to give your support. Let's continue. The question sounds simple, but it hides a wrong assumption. People hear, we went to the moon in 1969, so Mars should have been the next step. That sounds logical, but it is not how this works. The moon is not a smaller version of Mars, and Mars is not just the moon with more distance added on top. These are two very different missions, with very different rules, and that is where the misunderstanding starts. The moon was about 384,400 kilometers away, about 238,900 miles. That is far, and Apollo was one of the hardest things humans have ever done. But Mars is on a completely different scale. On average, Mars is about 225 million kilometers from Earth, around 140 million miles. And for a human mission, that distance does not just mean a longer flight. It means the whole mission changes shape. A moon mission is measured in days. A Mars mission is measured in years. That is the first thing people miss. The moon was a short mission by deep space standards. Apollo 11 was put on the path to the moon just 2 hours and 44 minutes after launch, and the crew got there in about 3 days. 3 days. That means the mission was built around short-term survival. You carry what you need, you move fast, you land, you leave, you come back. The timeline is tight, but it is still a short loop. Mars is not a short loop. A human Mars mission is expected to last about 3 years once you include the trip out, the long wait for Earth and Mars to line up again, and the trip back home. And that changes the meaning of the mission. Apollo was not easy, but it still happened close to home in space terms. If something went wrong, you were still in the Earth-Moon system. You were not millions of kilometers away with no fast way to get help. Mars removes that safety completely. Once you leave for Mars, you are committing to long-duration survival in deep space, not just a quick visit to another world. That is why saying, we did the moon, so why not Mars, skips over the biggest part of the problem. So the real issue is not just distance. The real issue is that distance changes the rules. At moon distance, Earth still feels close. Communication is quick. Mission control can respond fast. The crew still feels connected to the people on the ground. At Mars, that stops being true. Messages take many minutes to go one way. Help, advice, repair support. Even simple decisions all become slower and harder. During a Mars landing, that delay is so large that the spacecraft has to handle the landing by itself. Earth cannot react in time. By the time people on Earth know there is a problem, the spacecraft has already landed, or already crashed. That one fact changes the entire style of the mission. You are not just sending people farther away. You are sending people into a situation where they have to operate much more independently. The hardware has to do more on its own. The crew has to do more on its own. The mission has to survive without constant real-time support from Earth. That is not a small upgrade from Apollo. That is a different level of difficulty. Then you hit the next problem. Mars is not one challenge. It is a stack of separate hard problems that all show up in the same mission. The moon gave Apollo a brutal but cleaner job. Launch from Earth, cross space, orbit, land in a vacuum, leave the surface, come home. Mars adds a long interplanetary cruise, long-term radiation exposure, communication delay, rare launch windows, a dangerous landing through a thin atmosphere, freezing conditions, dust, lower gravity, toxic soil issues, and the need to survive on the surface for a long time without quick return. That is why the old comparison breaks down. The moon mission was a huge engineering achievement, but the structure of the mission was simpler. Mars requires everything at once. It needs a spacecraft for long-duration travel, a habitat for survival, systems for autonomy, protection against radiation, an entry and landing system that works on a planet with a thin but still dangerous atmosphere, and a return plan that still works after months or years away from Earth. That is not Apollo extended outward. That is a much bigger architecture. This is also why the idea that we somehow lost the ability to do it is not the real answer. The problem is not that humanity forgot how to go to space. The problem is that the Moon and Mars ask different questions. The Moon asked whether humans could leave Earth, reach another world, land and return. Mars asks whether humans can run a small self-contained survival system far from Earth for years, land heavy equipment safely, stay alive on the surface, and still make it home. Those are not equal questions, and the Moon itself helped create the misunderstanding. Apollo was so historic and so visually powerful that it made the next step look obvious. One world, then the next one. One landing, then a farther landing. But the first success made the second challenge look more proportional than it really was. It made people think the path would keep scaling in a simple way. It did not. Mars is not the next rung on the same ladder. It is a different ladder. That is the part hidden inside the question. The Moon was close, fast, and limited in duration. Mars is far, slow, delayed, and hostile over a much longer period. The Moon mission was about access. Mars is about sustained survival. The Moon was a short, high-risk expedition. Mars is a full campaign with no quick exits. Once you say it that way, the comparison starts to sound less convincing, because the missions stop looking similar. So the answer is not, we reached the Moon and then failed to repeat the trick farther away. The answer is that we solved one category of impossible mission, and Mars belongs to a deeper category. The first giant leap made the next one look like a natural follow-up. In reality, it opened the door to a much harder truth. Getting to Mars is not about doing Apollo again. It is about building something much more durable, much more independent, and much more resistant to failure. And once that becomes clear, the next question gets much more serious. If Mars is not just farther, then which part of the mission actually breaks the old Moon logic first? Is it the travel time, the delay, the landing, or the need to survive there for years? The answer starts with distance, because on Mars, distance does not just separate you from Earth, it turns the mission into isolation. Distance sounds like a simple number, but for Mars it changes the entire mission. That is the first hard break from the Moon. The Moon is far, but it is still close enough that the mission feels short, contained and recoverable. Mars is where distance stops being a travel issue and becomes a survival issue. That is why a Moon mission feels like a dangerous operation, but a Mars mission feels like separation. Not just from Earth as a place, but from Earth as support. The Moon is about a 3-day trip. That matters more than people think. 3 days means you can build a mission around getting there fast, doing the job, and coming back before the whole system starts breaking down under long exposure. Mars is different from the first second, because the crew is expected to be away for about 3 years. When you include the trip out, the wait on the surface for the planets to line up again, and the trip back. And once you stretch a mission from days into years, every basic question gets harder. Not slightly harder, completely harder. Food is different because now you are storing it for very long periods. Water is different because every kilogram matters, and recycling has to work at a much higher level. Oxygen is different because backup systems have to last much longer. Spare parts are different because now you are deciding in advance which failures you can survive and which ones will kill you. Exercise matters more. Medical planning matters more. Mental health matters more. Radiation shielding matters more. Even small things start to matter. Clothing, seals, filters, tools, cables, connectors, medications, waste systems, everything. On a Mars mission, the packing list starts to look less like a flight manifest and more like the inventory of a small moving world. That leads to the next problem. And this one is easy to underestimate. You cannot leave for Mars whenever you want. The Moon is always there in practical terms. Mars is not. Earth and Mars line up for the most efficient transfers only about once every 26 months. So if your rocket is not ready, if your life support system is not ready, if your landing system is not ready, if one major test goes wrong at the wrong time, you do not slip by a few weeks. You can slip by more than 2 years. That is a brutal rule. Mars does not care how close you are. Almost ready is not ready. And that one fact puts huge pressure on everything before launch. Budgets get stretched, crews have to wait, hardware ages, support can weaken, and whole programs can lose momentum because orbital mechanics will not give you a second chance on demand. That is one of the reasons Mars planning is so hard. It is not just engineering, it is timing. You need rockets, habitats, cargo systems, landing systems, crew systems, and return systems all to be ready inside a narrow corridor. On the moon, you still had constraints, but not this kind of long interval between serious opportunities. Mars turns scheduling into part of the danger. A delay on Earth can become a major setback in space before you have even launched. Then the question gets harsher. What happens if something goes wrong after launch? On the moon, that question is terrifying, but at least it lives inside a short mission. On Mars, there is no real resupply in the normal sense. There is no quick top-off. There is no rapid rescue. There is no realistic version of sending a replacement part next week and expecting it to matter. The farther you go, the harder it becomes to send instructions, supplies, medical support, repair hardware, anything. That means every failure has to be treated differently from the start. A broken valve on a moon mission is a major problem. A broken valve on the way to Mars can become a direct test of whether the entire mission was designed honestly. Did you bring enough redundancy, enough repair options, enough access to the damaged system, enough crew training, enough margin? Mars turns small failures into architecture questions, and that is why the speed comparison can be misleading. People hear the numbers from Apollo and they sound incredible, because they were. Apollo spacecraft was sent toward the moon at around 39,000 kilometers per hour, about 24,238 miles per hour. That is much faster than anything in everyday life. But Mars is not mainly a speed problem, it is a precision and endurance problem. Going fast is only one part. You also have to leave Earth cleanly, survive months of cruise, manage power and life support the whole way, arrive at the right place at the right angle at the right time, and still have enough control left to land on another planet. So the real challenge is not just velocity, it is staying functional across a long chain of events where one mistake early can ruin everything later. That is another reason the moon comparison hides more than it reveals. The moon mission can be understood as a fast, tightly organized loop. Mars is a sequence of linked missions pretending to be one mission. Departure, cruise, arrival, landing, surface survival, waiting period, launch from Mars, return cruise, Earth re-entry. Each part depends on the earlier parts going right, and each part adds time, stress, and exposure. So even when the spacecraft is moving at extreme speed, the mission still feels slow. Because the real enemy is not how fast you move through space, it is how long you must remain alive, healthy, and capable while moving through it. Then there is the part people do not always think about until much later, the psychological distance. On the moon, the crew is still mentally close to Earth. Communication is fast, the mission is short. And even under extreme pressure, there is still a strong sense that the ground is present with you. Mars reduces that. The farther you go, the less Earth feels like immediate support, and the more it feels like delayed advice. NASA has run analog studies with Mars-like communication delays reaching up to about 40 minutes round trip, because that is the kind of delay where the crew can no longer depend on Earth as an instant problem-solving partner, and that changes the culture of the mission in a very deep way. A Mars crew would not just be following instructions from home, they would become the final authority in many situations because there would be no practical alternative. If something breaks, they cannot pause reality and wait for Earth to walk them through it in real time. If someone gets sick, they cannot depend on a live team of specialists guiding every decision, second by second. If there is a systems emergency, they act first and explain later. That kind of autonomy is technical, but it is also psychological. It changes how crews are trained, how they make decisions, how much stress they carry, and how isolated they feel. And that may be one of the biggest differences of all. On the moon, you still feel like part of a mission being run from Earth. On Mars, the crew starts to feel like its own remote command post. That is a major shift, because it means exploration becomes less like remote control and more like true separation. The farther you go, the more the crew has to become its own mission control, its own repair team, its own emergency response unit, and its own final line of judgment. So when people ask why Mars is so much harder, distance is one of the first real answers. Because distance does not just mean farther travel. It means longer exposure, fewer chances, almost no resupply, slower help, tighter launch timing, more dependence on redundancy, and a crew that has to function with much more independence. The Moon still let us stay close to Earth in the ways that matter most. Mars takes that away. And once distance has done that, the next problem gets even worse. Because now Earth is not just far away, it is too far away to answer in time. By the time the signal comes back, the moment that mattered is already over. The next thing Mars takes away is control. That may be one of the most disturbing parts of the whole mission, because people are used to thinking that if something goes wrong, Earth can step in. That is how a lot of spaceflight looks from the outside. You picture a crew doing something difficult, mission control watching closely, experts talking constantly. And if a problem starts, someone on the ground helps solve it right away. Mars breaks that model. Not because the engineers are not good enough, and not because the radios are bad, but because the planet is too far away. The signal itself takes too long. By the time Earth answers, the event that mattered is already over. That is why Mars kills the fantasy of joystick exploration. You cannot fly a rover on Mars the way a person flies a drone nearby on Earth. NASA has been very clear about this for years. The communication lag is too long. You send a command, then you wait. The rover acts, then you wait again. There is no live steering in the normal sense. That is why missions like Perseverance have needed more and more onboard autonomy. The machine has to make local decisions, because Earth cannot react fast enough to do it moment by moment. This sounds like a technical detail, but it changes the feeling of the mission. On the Moon, you can still think in terms of rapid command and response. Earth still feels present. Mars removes that feeling. At Mars, every critical moment happens first, and only later becomes a conversation. That means the mission is no longer being actively flown from Earth in the way people often imagine. It is being supervised from far away, with a delay built into every choice. And once you understand that, the whole mission starts to look more dangerous, because distance is no longer just keeping you away from Earth, it is keeping Earth out of the moment when things go wrong. Then this gets much worse during landing. Mars entry, descent, and landing is one of the clearest examples of the delay problem becoming terrifying. People sometimes call it the 7 minutes of terror, and that phrase exists for a reason. During those minutes, the spacecraft is hitting the Martian atmosphere at extreme speed, dealing with heating, changing orientation, deploying a parachute, switching to powered descent, and trying to reach the surface in one piece. And all of this is happening while Earth cannot do anything in real time. Earth is basically receiving delayed news from a crisis that has already ended. For curiosity, entry began at about 5,900 meters per second, roughly 13,200 miles per hour. That is not a gentle arrival. That is a spacecraft hitting another world at hypervelocity and then trying to slow down through a sequence that has to work almost perfectly. The heat shield has to do its job. The timing has to be right. The parachute has to open correctly. The guidance has to stay locked in. The powered descent phase has to transition correctly. And none of that can depend on a human taking over from Earth at the last second, because the last second is long gone by the time the signal arrives. That is one of the biggest mental shocks in Mars exploration. You do not control the landing as it happens. You design the landing, you simulate the landing, you test the landing, you send the vehicle, and then you wait to find out whether the landing succeeded. That is a very different kind of confidence. It means you are not trusting your reaction speed. You are trusting the system completely. You are trusting sensors, software, hardware, sequencing, redundancy, and all the decisions made months or years earlier. By the time Mars starts judging the landing, the humans on Earth are already too late to change anything. And once you move from robotic missions to human ones, the delay becomes even more serious, because now it is not just a rover or a science payload at risk. Now it affects medicine, maintenance, and leadership. A Mars crew cannot depend on step-by-step support from Earth in the way people naturally want to imagine. If someone has a medical emergency, the crew cannot just wait for a full team of specialists to guide every action live. If there is a software fault in a critical life support system, the crew cannot freeze the situation and wait for a committee on Earth to decide what to do. If dust starts affecting power systems, or a pressure issue appears in a habitat, or a surface vehicle has a failure far from base, the crew will be making the first decisions alone. That means autonomy is not just a feature of the spacecraft, it becomes part of human operations. The crew has to diagnose problems, make decisions, manage risk, and carry authority in a much stronger way than crews in low Earth orbit or even lunar missions. NASA has done work with Mars-like delay conditions for exactly this reason. Once the round-trip delay gets large enough, something basic changes. Earth stops being immediate support and becomes delayed support. That does not mean Earth is useless. It means Earth is no longer part of the same moment, and that forces a completely different mindset. A Mars crew would need to function more like a remote expedition team than a crew constantly backed by live control rooms. They would need broader training, stronger procedures, and a mission culture built around local judgment. Leadership changes under those conditions. Responsibility changes. Even the emotional pressure changes. Because the crew knows that for many serious situations, they are the first answer, not the last step before Earth answers. And robotic Mars missions have been teaching this lesson the whole time. Every time NASA gives a rover more ability to navigate, assess terrain, or plan motion locally, it is not just making a better robot. It is responding to the basic truth that Mars is too far away for real-time teleoperation. Perseverance is part of that pattern. As Mars missions become more capable, the onboard systems have to become more capable too, because waiting on Earth for every small decision wastes time and, in some cases, makes the mission impossible. That matters beyond robotics. It tells you what a human Mars base would need. It would need diagnostic systems that can reason locally, planning tools that can help crews solve problems on site, navigation systems that do not depend on constant Earth input, and emergency systems that keep working even when the ground team is still receiving the first reports. In that sense, Mars is testing something very important. It is testing whether our technology can be trusted to operate far from us, and whether crews can be trusted to manage advanced systems without immediate outside control. That changes the old image of exploration in a very direct way. People like the idea that Earth is guiding every step, always watching, always ready, always one sentence away from helping. Mars breaks that image. At Mars, exploration becomes delayed, distributed, and partly handed over to the crew and the machine. Some control stays on Earth, but a meaningful part of it moves outward because it has to. There is no communication upgrade that fixes this. There is no better headset, no faster computer, no stronger antenna that removes the light time delay between planets. This is not a technology failure. It is the solar system enforcing its own limits. And that may be the most unsettling part of all. We are used to thinking that better technology solves distance. In many cases, it does. Mars is where that confidence runs into physics. Light only moves so fast. Signals only move so fast. You can improve software, improve antennas, improve compression, improve onboard systems, but you cannot make Earth and Mars stop being far apart. You cannot negotiate with light speed. So the delay is not a temporary obstacle in Mars exploration. It is part of the permanent operating environment. That is why Mars feels different from the Moon at such a deep level. The Moon still lets you believe Earth is close enough to stay inside the mission. Mars forces you to accept that Earth is outside the moment when the most important things happen. And once you lose real-time control, the next question becomes even more dangerous, because if Earth cannot guide the landing as it happens, then what exactly are you landing through? The answer is one of the cruelest parts of Mars. It has just enough atmosphere to make arrival violent, and not enough to make it easy. The landing is where Mars stops looking difficult and starts looking unfair. The Moon gives you one clear problem. There is no real atmosphere. So you know what has to slow you down: rockets. That is hard, but it is direct. Mars is worse because it gives you part of what you need, but not enough. Its atmosphere is real, but thin, only about 1% of Earth's surface pressure on average, and that creates one of the worst combinations in spaceflight. There is enough air to slam into at extreme speed and generate huge heating, but not enough air to make landing simple. So Mars does not let you ignore the atmosphere, and it does not let you rely on it either. That is why Mars is a trap. If there were no atmosphere like the Moon, you would plan around pure rocket descent. If the atmosphere were thick like Earth, You could get much more braking from it. Mars sits in between, in the most frustrating way possible. You arrive at another planet moving at extreme speed. You hit enough air to turn entry into a violent heating problem, but when you need that same atmosphere to save you, it is too thin to do the full job. So from the start, Mars gives you the worst of both systems. It makes entry dangerous, and it still leaves you with a major landing problem at the end. That becomes very clear when you look at how fast these spacecraft arrive. For Mars Science Laboratory, the mission that carried Curiosity, the spacecraft hit the top of the Martian atmosphere at about 5.9 kilometers per second. That is around 5,900 meters per second, or roughly 13,200 miles per hour. This is not a controlled glide into an airport approach. This is a hypervelocity entry. The spacecraft is arriving so fast that the first challenge is simply surviving the atmosphere long enough to keep going. So now think about what has to happen next. The heat shield has to absorb enormous energy. The spacecraft has to stay stable. The timing has to be right. Then the whole system has to transition through multiple stages in just minutes. JPL noted that Curiosity's landing sequence used 6 different vehicle configurations and 76 pyrotechnic devices. That number matters because it shows you what Mars landing really is. It is not one landing move. It is a chain of critical events, one after another, with very little time to recover if anything goes wrong. One separation event fails, one sensor reads wrong, one timing issue slips, one deployment goes bad, and the mission can be over immediately. That is what makes Mars landing so tense. The problem is not just difficulty. The problem is compression. A huge amount of risk is packed into a very short period of time. The spacecraft has to do many different things in the correct order while moving from extreme speed to zero on another planet, through an atmosphere that is helping a little, hurting a lot, and never becoming simple. That is why the famous phrase 7 minutes of terror stuck. It sounds dramatic, but it is also accurate. Those minutes contain enough complexity to destroy years of work in seconds. Then comes the part that sounds helpful until you look closer. Parachutes. Yes, Mars has enough atmosphere for a parachute to matter, but the key word is matter, not solve. Even a supersonic parachute can only do so much there, because the air is too thin. So parachutes help reduce speed, but only for part of the descent. They do not finish the job, especially for heavier payloads. That means you still need powered descent near the end, which adds more engines, more control logic, more fuel management, and more failure points. And this is where the warning for human missions becomes very serious. Curiosity and Perseverance are not human-sized missions. They are robotic missions, and even they pushed older landing methods to the limit. Airbags were no longer enough for rovers of that size. Simpler systems ran out of room as the mass went up. That is why NASA used the sky crane system, because landing a heavy rover safely had already become too hard for older approaches. So if landing a car-sized robot needed something that intricate, then landing a human habitat, cargo systems, life support equipment, surface power systems, and a future ascent vehicle is a much larger problem. The scale does not increase neatly. It becomes much harder because more mass means more momentum, more energy to remove, and fewer easy options. That is the point where people often realize Mars landing is not a solved problem waiting for a launch date. It is still one of the biggest open parts of the architecture. Small robotic payloads are hard. Large robotic payloads are harder. Human-class payloads move into another category. You are no longer trying to set down one rover. You are trying to land the equipment needed to keep people alive, and you need it to arrive intact, in the right place, ready to work with much tighter safety margins. Then there is the most honest evidence of all, the historical record. Mars does not just look difficult in theory, it has repeatedly proved it in practice. JPL's InSight landing material pointed out that at that time, only about 40% of all Mars missions ever launched by any space agency had succeeded. That number is one of the most sobering facts in all of planetary exploration, because it means Mars has not merely challenged engineers. It has beaten them many times across different countries, different programs, different decades, and different mission designs. That record matters because it removes any temptation to treat Mars as a routine destination with some added complications. Mars has a real history of punishing mistakes. Some missions were lost at launch, some were lost in navigation. Some were lost during entry, descent, and landing. Some were lost because of software, because of system design, because of assumptions that turned out to be wrong. So when people talk about Mars having a reputation, that reputation is not based on myth. It is based on a scoreboard. And for human missions, that scoreboard becomes even more uncomfortable. Because humans do not just need the spacecraft to survive impact-free. They need the landing to be precise, stable, and operationally useful. A rover can land and begin a science mission. A human landing has to do more than that. It has to deliver systems that support life. It has to arrive close enough to pre-positioned supplies or landing zones that the whole surface plan still works. It has to avoid damage that could turn a successful landing into a failed stay. And it has to do all of this with much lower tolerance for risk. Because now failure is not just the loss of hardware, it is the loss of crew. That is why NASA planning keeps putting so much attention on atmospheric measurements, winds, density prediction, and landing conditions. The Martian atmosphere is not only thin, it is variable. That means the spacecraft is not descending through a perfectly fixed environment. It is descending through a changing one. Small differences in density, winds, and weather can affect a landing sequence that already has very little room for error. And when you are trying to land larger payloads, those uncertainties matter even more. So landing on Mars is not just the final step before surface operations begin. It is one of the main unsolved problems of the whole mission. You cannot treat it like a box to check after cruise. It is one of the places where the entire architecture is forced to prove itself. Because if you cannot land the mass you need, safely, precisely, and repeatedly, then a human Mars mission is not ready, no matter how advanced the rockets look on the launch pad. And once you accept how violent and delicate the landing really is, the next problem gets even darker. Because even if you land successfully, the environment does not relax. The danger keeps going silently, every hour, every day, all the way through the mission. Because the space between Earth and Mars is not empty, and Mars itself is not safe. It is full of radiation. And that means the mission is not just fighting distance and landing, it is fighting time inside a hostile environment that keeps reaching into human biology. Radiation is where Mars stops being only an engineering problem and becomes a human body problem. Rockets, landing systems, habitats, all of that is hard, but radiation is different because it does not need a dramatic failure to hurt you. It works quietly, it builds over time. And that is exactly why Mars is so serious. Apollo crews went through radiation, but only for days. A Mars crew would live in that environment for months during the trip, then keep taking exposure on the surface, then take more on the way back. So this is not a brief pass through danger. It is long-term exposure as part of the mission design. That difference is one of the clearest lines between the Moon and Mars. Apollo was fast enough that radiation was dangerous, but limited by time. Mars removes that protection. During cruise to Mars, Curiosity's radiation assessment detector measured about 1.8 millisieverts per day from galactic cosmic rays. On the Martian surface, the same instrument measured about 0.65 to 0.7 millisieverts per day. That surface number is lower, but it is still serious when you add it up over long periods. And that is the key point. Mars is not just far away. It keeps you inside a radiation environment long enough for the accumulated dose to matter in a much deeper way. So yes, Mars has an atmosphere. And yes, that atmosphere helps a little. It gives some shielding compared with open deep space, which is why the daily dose on the surface is lower than during cruise. But lower is not the same as safe. That is a very important distinction. Mars does not protect you the way Earth protects you. Earth has a thick atmosphere and a global magnetic field. Mars does not. NASA's human risk work has made this clear. Surface exposure on Mars can be roughly in the range of ISS daily dose in some cases, while deep space transit can be 2 to 3 times ISS levels. And that comparison matters because the ISS still sits inside low Earth orbit, still relatively close to Earth, still protected in important ways by Earth's magnetosphere, and still available for rapid evacuation compared with Mars. A Mars mission has none of those comforts. The crew is farther away, more exposed, and stuck with the dose they take. That is where the trade-offs become harsh. Every kilogram of shielding helps, but every kilogram also has to be launched, carried, and in many cases landed. So radiation protection is not something you solve by just adding more mass without limit. If you add more shielding, you may have to remove something else. Cargo, scientific equipment, spare parts, fuel margin, life support margin. And that means radiation is not only a medical concern, it is a mission design fight over mass, volume, priorities, and risk. Then there is the more unpredictable threat. Solar storms. Galactic cosmic rays are the steady background problem. They are always there, adding dose day after day. Solar particle events are different. They are the sudden threat. They can deliver a sharp radiation spike over a much shorter period, and that makes them one of the biggest uncertainties in planning human Mars missions. NASA's RAD work has stressed that these solar events remain a major unknown in predicting the full risk, because a bad event during cruise could be very dangerous. On Earth, a lot of that threat is absorbed or deflected by the planet's magnetic field and atmosphere. On a Mars mission, especially during transit, the crew does not have that protection. They are inside a spacecraft, far from Earth, hoping the storm shelter strategy is good enough for the event they actually get, not the event they wish they got. That is one of the hardest parts of the radiation problem. You are not only planning for the average dose, you are planning for the bad day. And the bad day may come at a terrible time during cruise, when the crew is in a small volume, when there is no fast rescue, and when the spacecraft itself may not have much extra shielding to spare. So the mission cannot just think in terms of long-term exposure, it also has to think in terms of emergency exposure, sudden spikes, and how quickly the crew can get into the best protected part of the vehicle. Once you take that seriously, radiation starts spreading through the entire spacecraft design. It is not something that stays inside one chapter labelled health risks. It affects where the crew sleeps, where the water goes, where food is stored, how waste is stored, where the storm shelter is located, what the internal layout looks like, and even what materials get placed around the crew during transit. Water is not just water anymore. It may also be shielding. Food is not just food anymore. Its storage location may help protect the crew. Waste is not just waste anymore. Even that can become part of the shielding logic if the mission is designed that way. And this continues after landing. If the crew lives on Mars for a long period, the habitat itself may need protection from local material. That leads to ideas like using Martian soil or regolith to cover parts of the habitat, because local material could help reduce exposure. Old NASA Mars studies even looked at how mission propellant and overall spacecraft arrangement could be used as part of radiation protection. That tells you how deep the problem goes. Radiation does not just affect medical charts. It shapes the physical structure of the mission. It changes the spacecraft, the habitat, the cargo layout, and the operations plan. That is why radiation is so important in the Mars story. It is not dramatic in the way a landing failure is dramatic. It does not announce itself with one loud event most of the time. It is constant, quiet, and cumulative. That makes it easy to underestimate if you are only thinking in cinematic terms. But for a real Mars mission, every extra day is another day of dose. Every delay matters. Every long stay matters. Every design shortcut matters. Time itself becomes part of the hazard. And that is where Mars starts losing the old heroic image people project onto it. Once you really look at the numbers, the idea of simply going there, planting a flag, and calling it done starts to sound shallow. Mars is not just a far destination waiting for visitors. It is an environment where the journey hurts you, the surface keeps exposing you, and the mission architecture has to fight that from beginning to end. The problem is not only getting there. The problem is what the trip and the planet do to the human body while you are there. So radiation changes the emotional meaning of Mars. It stops being only a question of courage and starts becoming a question of biology, shielding, exposure limits, and system design. It reminds you that interplanetary space is not empty in the human sense. It is full of things that can pass through metal, pass into tissue, damage cells, and increase risk over time. That is why Mars is not just testing whether we can travel farther. It is testing whether we can keep human beings healthy enough across a mission long enough to matter. And even after all of that, radiation is still not the full story of surviving on Mars, because once you reach the surface, another set of problems begins. The gravity is weaker, the cold is relentless, the dust gets everywhere, and the planet looks simple from a distance but becomes much more hostile up close. Mars is not just dangerous on the way there, it stays difficult after you land. Mars does not become simple after landing. In some ways, that is when the mission becomes more complicated, because now you are no longer just trying to survive a trip. You are trying to live and work inside an environment that keeps pushing against your equipment, your schedule, and your body. From orbit, Mars can look like a dry, rocky desert. On the ground, it behaves more like a hostile test chamber. Almost every basic condition is close enough to feel familiar for a second, then different enough to become a problem. Start with gravity, because it sounds like one of the few advantages. Mars gravity is about 3.71 meters per second squared, around 38% of Earth's gravity. That means things weigh less. Cargo is easier to move. Climbing may be easier. Launching back off the surface needs less energy than launching from Earth. All of that is useful, but lower gravity is not a free benefit, because the human body is not designed for Mars gravity. And this is where the problem becomes uncomfortable. We know a lot about Earth gravity. We know a lot about microgravity from long stays in orbit. Mars sits in between, and that middle zone is still a major unknown. That matters because partial gravity may still be too low to prevent many of the problems seen in space. Muscle loss, bone loss, circulation changes, balance issues, and other long-duration effects may still happen, but we do not yet know exactly how Mars gravity changes the picture over many months or years. The Moon is even lower, about 1.624 meters per second squared, but Apollo stays were too short to teach us what long-term adaptation would really look like. So Mars puts humans into a gravity regime that sounds helpful in engineering terms, but remains medically uncertain. That is a serious issue, because if the crew slowly weakens on the surface, then surface work, emergency response, and the trip home all become harder. Then there is the cold, and on Mars the cold is not a side issue. It is constant pressure on the whole mission. NASA lists the average surface temperature at around minus 53 degrees Celsius, about minus 64 degrees Fahrenheit. But averages do not tell the whole story. Conditions can drop to around minus 128 degrees Celsius, about minus 199 degrees Fahrenheit during polar night, and rise to around 27 degrees Celsius, or 80 degrees Fahrenheit, near the equator at midday, under favourable conditions. That is a huge range, and every piece of hardware has to survive inside it. Habitats, batteries, seals, wiring, lubricants, electronics, rovers, suits, airlocks, all of it. This matters because Mars does not just get cold, it forces your systems to keep fighting temperature all the time. Heat has to be preserved where humans live. Electronics have to stay inside operating limits. Moving parts have to keep working without becoming brittle or inefficient. The Moon also has brutal temperature swings, but Mars adds more variables. It has an atmosphere. Thin but real. It has dust. It has weather patterns. It has seasons. So the thermal problem is not just about day and night. It is tied to a larger environmental system that keeps changing around your mission. Then you get to one of the strangest parts of Mars. The day feels almost familiar, but the year does not. A Martian day is 24 hours, 39 minutes, and 35 seconds. That is close enough to Earth that people can adapt to it much more easily than many first assume. In fact, that is one of the few ways Mars can seem almost friendly. A day is only about 39 minutes longer than on Earth. But then the larger calendar starts pulling away. A Martian year lasts 687 Earth days, and Mars has seasons because its axis is tilted by about 25 degrees, similar in principle to Earth's tilt. That means a surface mission is not operating on a simple Earth-style timeline. Seasonal changes stretch over much longer periods. Dust conditions can shift over long intervals. Temperatures change over a long year. Solar power availability can change with season and weather. So Mars gives you one rhythm that feels familiar, the day, and surrounds it with a much bigger pattern that is very different. That can affect planning in major ways. A habitat that works well in one season may face different power or temperature pressures later. Surface operations, travel windows, power management, and long-term maintenance all have to account for a calendar that does not behave like Earth's. Then there is the dust. And this is one of those Mars problems that gets simplified too much. People hear about dust storms and picture something like an Earth hurricane. That is not quite the right way to think about it. NASA points out that winds on Mars can be fast, but because the atmosphere is only about 1% as dense as Earth's, the force of that wind is much weaker than the same wind speed would be here. So Mars dust storms are strange. They can grow to enormous scale, even planet-encircling scale, and still not hit like a dense Earth storm in pure force. But that does not make them harmless. It just makes their danger different. The real issue is not mainly getting knocked over by wind. The real issue is what fine dust does over time. Dust can settle on solar panels and reduce power. It can coat optics and damage visibility. It can get into seals, joints, radiators, and moving mechanisms. It can interfere with thermal control. It can contaminate habitats if it gets inside. And because Mars missions depend so heavily on reliability, a fine abrasive material that keeps spreading across equipment becomes a systems-level enemy. It is not one dramatic event. It is persistent interference with everything you need to keep alive and keep working. That also raises a human issue. If dust enters habitats or equipment repeatedly, then it becomes a contamination problem, not just a maintenance problem. Filters matter more. Cleaning matters more. Suit design matters more. Airlock design matters more. On Mars, even the dirt becomes part of mission architecture. You cannot treat it as scenery. And then there is the atmosphere again, showing up in a completely different way. Flying on Mars sounds almost ridiculous until you look at what Ingenuity had to do. Ingenuity proved powered flight on another planet, and that was a major achievement. But it also showed how hard Mars makes even small successes. The atmosphere is less than 1% as dense as Earth's, so to generate enough lift, Ingenuity needed large rotor blades spinning at roughly 2,400 revolutions per minute. That is an extreme solution just to make short flights, around 5 meters or 15 feet high in many of its early hops. That is the lesson hidden inside that success. Mars does allow things to work, but usually in a strained way. Machines do not operate there with easy margin. They operate close to the edge of what the environment allows. Flight is possible, but only with a vehicle designed very specifically for thin air. Surface travel is possible, but every wheel, motor, and seal has to endure cold, dust, and terrain. Human activity is possible, but only inside layers of protection. Mars keeps forcing you to build systems that are not merely capable, but extremely well adapted to conditions that resist simple solutions. So when people say Mars looks like a desert, that is only partly true. A desert on Earth is still part of Earth's life support system. Mars is not. It has some familiar features: ground, horizons, day and night, seasons, wind, dust, but they do not add up to a familiar place. They add up to a place where almost every normal activity must be engineered back into existence. Warmth has to be created, pressure has to be created, breathable air has to be created, clean indoor environments have to be protected, mobility has to be preserved against dust and cold, and the human body has to function in gravity we still do not fully understand. That is why the surface of Mars is not the easy part after the hard landing. It is the next test. It asks whether your systems can keep working day after day in an environment that keeps wearing them down, and whether your crew can stay healthy and effective while living inside those limits. Mars does not just challenge arrival, it challenges routine, and that is sometimes even more dangerous, because routine is where missions start relying on everything continuing to work, and that leads straight into the next problem, because surviving on the surface is still not enough. A Mars mission is not complete when you land, and it is not complete when you stay alive there. It only counts if you can leave. And that means the hardest hidden demand of all may be this one. Getting home from Mars means carrying a second mission inside the first. Getting to Mars is only half the mission, and that is one of the biggest reasons people underestimate how hard it is. The public version of a Mars mission usually ends at landing. The rocket launches, the spacecraft arrives, the crew steps onto the surface, and that looks like the payoff. But for a real mission, that is not the payoff. That is the midpoint. Because Mars does not just ask whether you can arrive, it asks whether you can stay alive long enough to leave, launch from another planet, survive another long trip, and then come back through Earth's atmosphere in one piece. The return is not a bonus round. It is built into the meaning of success. That is one of the biggest differences from Apollo. The moon missions were designed as short loops. You launched from Earth, travelled for a few days, landed, stayed for a short period, lifted off, met the command module, and came home. The ascent from the moon was serious, but the overall structure was still compact. The moon's gravity is low, the surface has no atmosphere, and the whole mission was built around quick return. That matters because it kept the loop clean. You were not building a long-term presence. You were completing a fast and very difficult expedition. Mars is not like that. The phrase "go to Mars" sounds simple, but it hides several missions inside one sentence. First, you have the trip out, which is already a long deep space mission. Then you have surface operations, which are their own survival problem. Then you have to launch from Mars, which is another major spaceflight event. Then you have the return cruise, which means another long exposure to space, more radiation, more system wear, more risk. Then finally, you still have to re-enter Earth's atmosphere safely. So Mars is not one mission stretched farther. It is an outbound mission, a surface campaign, an ascent mission, and a return mission, chained together so tightly that failure in one part can destroy the rest. That becomes even more serious when you remember launch windows. You cannot just leave Mars whenever you want. Just like departure from Earth depends on planetary alignment, the return depends on it too. That means many mission plans involve astronauts staying on Mars until the solar system gives them the right geometry to leave. So the return is not a matter of deciding it is time to go home and firing the engines. It is a matter of surviving on Mars until departure becomes possible. That changes the emotional logic of the mission immediately. The crew is not just landing on Mars, they are committing to remain there until orbital mechanics allow the next step. The planets become the timetable, and that means the return architecture has to sit there and wait with them, or be ready for them later, and still function perfectly when the moment finally comes. Your ascent vehicle has to remain viable. Your fuel strategy has to remain viable. Your habitat has to remain viable. The crew's health has to remain viable. Every delay, every bit of wear, every maintenance challenge, every environmental stress becomes part of the return story before the return even begins. This is why getting home from Mars is not just a transportation problem. It is a long-term reliability problem. A Mars ascent vehicle would likely sit on the surface through cold, dust, and long exposure before anyone asks it to do the most important thing it will ever do: ignite and work correctly. That is a brutal requirement. It is not enough to design a vehicle that works in tests or works shortly after landing. It has to keep working after months or even years in a difficult environment. Fuel systems have to stay stable. Engines have to remain healthy. Seals, valves, electronics, guidance, structure, all of it has to survive the wait and then perform at the exact moment the crew's lives depend on it. That part does not always get as much attention as landing, but it may be one of the harshest tests in the entire mission. Landing is dramatic, so people focus on it. But ascent from Mars is where the architecture has to prove that it was honest from the beginning. If the return vehicle cannot survive the environment, if it cannot be maintained, if it cannot ignite reliably after a long stay, then the whole mission concept starts to fall apart. Apollo's lunar ascent stage had to work after a short stay on the moon. A Mars ascent vehicle would be living through a much longer and more punishing story before anyone climbs inside it to leave. That is one reason serious Mars planning keeps coming back to in situ resource utilization. If you try to bring every kilogram of return propellant from Earth, the mission becomes extremely heavy and expensive very quickly. So planners keep looking at ways to make some of what is needed on Mars itself, especially using the Martian atmosphere, which is mostly carbon dioxide, along with local resources if they can be accessed. That idea is not there because it sounds futuristic. It is there because the mass problem is real. If Mars is going to support repeated human missions, or even one mission with better margins, then using local materials for oxygen or fuel starts to look less like an extra feature and more like part of the logic of getting home. And even before humans try it, robotic Mars sample return planning has already shown how hard this whole category of problem is. Bringing a few sealed tubes of Martian rock back to Earth sounds simple when you say it quickly. In practice, it has pushed mission planners toward extremely complicated architectures involving landers, orbiters, sample handling, caching strategies, rendezvous logic, and a launch from Mars itself. That is just for rocks, not people, not habitats, not life support, not a crew that needs to survive the whole chain, just a small scientific payload. That is the warning hidden in sample return. It shows that bringing something back from Mars is not a small add-on to exploration. It is one of the main engineering battles. If returning a limited robotic payload already demands that much coordination, then returning human beings multiplies the complexity by a huge amount. More mass, more risk, more systems, tighter safety requirements, more consequences if anything fails. So when people picture return as the final chapter, they are missing the structure of the story. Return is not the epilogue. Return is one of the central plots. And that is the point where Mars stops feeling like a destination and starts feeling like a campaign. A destination sounds like a place you go to. A campaign is something with stages, waiting periods, dependencies, stockpiles, timing rules, and no fast exit. That is much closer to what Mars really is. You do not just travel there. You pre-position, you synchronize. You preserve equipment, you manage surface operations, you protect the return path, and you hope every phase still supports the next one when the time comes. That is why the emotional comparison with Apollo is so strong, but technically so misleading. Apollo proved that humans could leave Earth, land on another world, and return from a short-range mission of extreme precision and courage. Mars asks something broader and harder. It asks whether humans can build a closed-loop interplanetary expedition, where travel, survival, launch, and return all remain connected for years without breaking. That is a much bigger standard, not just reach another world, but function across worlds. So the return problem changes how you see the whole mission. It tells you that a Mars landing is not the end of the hard part. It may not even be the hardest part. Because a crewed Mars mission is only successful if every earlier decision still holds together when it is finally time to leave. If the ascent vehicle fails, if the fuel plan fails, if the habitat degrades too much, if the crew's health falls too far, then the mission does not end heroically. It just stops on Mars. And that is where the tension gets worse. Because once the mission depends on so many linked systems staying alive across such a long chain, even a small weakness can spread through everything. Mars is not just hard because it is far. It is hard because it gives mistakes more time to grow, more systems to infect, and fewer chances to recover. The farther you go, the less forgiving failure becomes. Mars is not just hard when everything goes wrong. Mars is hard because even small things can go wrong for too long. That is a major difference from the Moon. A short mission can survive on tighter margins because the systems only need to hold together for a limited time. Mars keeps the mission under stress for months, then for more months, then for more months again. And once you stretch the timeline that far, reliability stops being a background issue. It becomes the mission. The first warning is the actual record. Space agencies do not have to guess whether Mars is unforgiving. The history already answered that. JPL's InSight material noted that only about 40% of Mars missions had succeeded historically at that point. That number matters because it removes any comforting illusion that Mars is just another destination with a bad reputation. Mars has repeatedly defeated missions for real reasons. Launch failures, navigation errors, entry problems, software mistakes, communication losses, system breakdowns. This is not one country making one mistake. This is a pattern across decades of exploration. The planet has punished weakness again and again. That is why the success rate matters more than any dramatic phrase. It tells you Mars is not difficult in an abstract way. It is difficult in the practical sense that missions really have been lost there, and robotic missions are already allowed to accept risks that no human mission could ever accept. So if the robotic record has been that harsh, then crewed missions have to be designed to a much higher standard. Not a little higher, much higher. Then you get to the deeper reason. Complexity gets worse over time. A short mission can sometimes get away with fewer operating modes, fewer spare parts, and fewer opportunities for parts to age into failure. Mars does not give you that luxury. A Mars mission is a long chain, which means every system gets more chances to drift, wear down, or fail at the wrong moment. Valves open and close more times, seals sit under stress for longer, batteries go through more thermal cycles, software sees more unusual situations, filters clog, lubricants age, wiring deals with more heating and cooling cycles. Human beings get tired, and tired crews are also part of the reliability picture. That is the part people often miss. Reliability is not just about whether the hardware was tested well on day one. It is about whether the system still works after months of operation, months of wear, months of exposure, months of small problems piling up. The farther you go and the longer you stay, the more reliability becomes a slow fight against time. That is why NASA's idea of distance as a hazard is really a reliability warning. Distance means you cannot quickly swap equipment, cannot quickly repair from Earth, cannot quickly escape. So every weakness lasts longer, and every weakness matters more. And Mars is especially dangerous because it hates single points of failure. You can already see that in robotic landings. Curiosity's landing sequence alone involved multiple vehicle configurations and 76 pyrotechnic devices in a short period. That is a huge concentration of mission-critical events compressed into minutes. For a human mission, that lesson becomes even sharper. Redundancy cannot just exist on paper. It has to be real. It has to be layered. It has to survive off-nominal conditions, not just normal ones. That means you cannot accept hidden dependencies that quietly hold the whole mission together until one part breaks. You cannot build a Mars architecture where one valve, one line, one controller, one software path, one power bus, one thermal loop, or one access point becomes the thing that silently decides whether the crew lives or dies. On Mars, single-point failures are not a sign of bold engineering. They are a sign that the design is not mature enough yet. That leads straight into maintenance. And this may be one of the least glamorous, but most important parts of the whole problem. On a robotic mission, a failure can end science. That is disappointing and expensive. But the mission is over in one sense only. On a crewed Mars mission, a failure can threaten lives. That changes what acceptable maintenance even means. The system cannot just be high performance when everything is normal. It has to be repairable when things are not normal. That means crews need tools, access panels, replaceable parts, diagnostic systems, and training broad enough to deal with problems that are usually handled by large teams on Earth. A box that works beautifully in laboratory conditions, but is impossible to open in the field, is not good enough. A system that performs very well, but cannot be repaired by exhausted astronauts in partial gravity, is not good enough. A critical unit that requires special factory conditions to replace is not good enough. Mars pushes engineering away from the mindset of works great when untouched, and toward the mindset of survives damage, survives wear, and can be fixed under pressure. That is a very different engineering culture. It puts a premium on access, modularity, simplicity, where possible, graceful failure modes, and realistic repair procedures. The crew may be dealing with dust contamination, communication delay, limited tools, limited spare parts, and fatigue all at once. So the machine cannot just be advanced. It has to be maintainable in real mission conditions. And that is a much harder standard than normal high-performance design. This is where Mars may force a new level of design maturity. The Moon let us do an extreme mission with huge precision and courage, but it was still focused and relatively short. Mars may require systems so mature, resilient, and failure-tolerant that they change the way deep space hardware is designed across the board. Not because engineers suddenly became more careful, but because Mars gives weak design nowhere to hide. If a system is fragile, Mars will find that out. If a maintenance plan is unrealistic, Mars will find that out. If redundancy is superficial, Mars will find that out. So Mars acts like a filter. It exposes every bad assumption that can be covered up on shorter missions. It exposes overconfidence. It exposes optimistic maintenance logic. It exposes hidden dependencies. It exposes designs that only work beautifully in nominal conditions. That is one of the biggest conceptual jumps in this whole story. Mars is not just the next target after the Moon. It is a harsher test of whether human spaceflight systems are truly ready to operate far from Earth without breaking down. And that changes the meaning of the mission again. The challenge is no longer just bravery, speed, or launch power. It is design honesty. Did the mission planners really account for long duration wear, real repairs, true redundancy, and delayed help? Or did they build something that only looks strong on presentation slides? Mars makes that question unavoidable. That is why reliability may be one of the most important answers to the whole Mars question. The Moon let us perform a short, focused, extraordinary operation. Mars demands a system that keeps functioning through time, damage, delay, and uncertainty. The farther you go, the less room there is for fragile brilliance. What you need instead is hardware, software, and operations mature enough to keep working after the exciting part is over. And once you push the mission to that level, another problem comes into focus, because even if your systems are reliable, you still cannot carry everything from Earth forever. At some point, the mission has to stop behaving like a visit and start behaving like the beginning of local survival. And that means Mars is not only a reliability problem, it is also a resource problem. The resource problem is where Mars stops being a travel mission and starts becoming a survival system. On the Moon, you can still think like a visitor. The trip is short, the return is fast, and brute force logistics can carry a lot of the mission. You pack what you need, use it, and come home. Mars breaks that logic very quickly. The distance is too large. The mission is too long, and the mass penalties are too severe. You cannot carry a whole world with you, even though that is exactly what the crew would want. That is one of the hardest realities in Mars planning. Every kilogram launched from Earth creates more work for the rest of the mission. It has to be lifted off Earth, pushed through space, landed on Mars, stored, protected, possibly lifted off Mars again, and in some cases supported all the way through return. So mass does not stay local to one part of the architecture. It multiplies through everything. A little more cargo on paper can mean much bigger demands on launch systems, fuel, landing systems, and surface operations. That is why the old strategy of just bringing more stops scaling well once you move from the Moon to Mars. For a short lunar mission, brute force logistics can still dominate the design. For Mars, that approach starts collapsing under its own weight. The deeper the mission goes, the more obvious it becomes that local resources are not a luxury idea. They are part of the difference between a mission that closes mathematically and one that turns into a supply chain fantasy. That is why serious Mars planning keeps circling back to the same question. What can the planet itself provide? Then you look at the atmosphere, and Mars gives one of its most frustrating answers. The atmosphere is terrible for humans. It is mostly carbon dioxide, far too thin to breathe, and on average only around 1% of Earth's surface pressure. That makes it useless as direct life support, and only partly useful for landing. But chemically it may still be valuable. The same atmosphere that does not keep you alive could help provide the raw material for oxygen production and possibly return propellant through in situ resource utilization systems. That is a major shift in thinking. The atmosphere stops being only a hazard and starts becoming feedstock. That is one of the most important ideas in Mars architecture, because it turns the environment from a pure burden into a partial supplier. If you can pull useful oxygen out of Martian carbon dioxide, then the mission gains options. If you can connect that oxygen production to fuel strategies, then the return side of the architecture starts looking more realistic. Suddenly the atmosphere is no longer just a thin layer that makes landing difficult. It becomes something the mission might process, store, and rely on. That is also one of the most Mars-specific ideas imaginable. The planet is hostile, but some of the same conditions that make it hostile may also provide what the crew needs. The atmosphere is trying to kill you if you walk into it unprotected, but it may also contain some of the raw material that helps your systems keep working, and maybe even helps you get home. That does not make Mars generous. It makes Mars usable only if your technology is good enough to force value out of an environment that was not built for you. Then there is water. And on Mars, water is much more than drinking supply. Water matters for drinking, obviously, but also for hygiene, food production, chemical processing, radiation shielding, and fuel-related systems. That means water is not one-line item in the cargo manifest. It is part of almost everything. If accessible water ice exists in useful places, then it can affect where you land, how you build habitats, how you protect the crew, and how much you need to launch from Earth. That is why mapping ice and studying subsurface resources matters so much. From the outside, that can sound like geology research. For a real mission, it is much more than that. It is resource mapping for survival. A future crew may need to dig part of its safety out of the ground. That changes the meaning of exploration. You are not just studying the planet to understand its past, you are studying it because the local environment may become part of your life support chain. On Mars, geology is not just science. Geology is logistics. And this is where the resource problem becomes more realistic and more difficult at the same time. It is true that Mars may offer useful carbon dioxide and useful water ice, but that does not mean the resources are easy to use. The slogan "Live off the land" sounds simple until you ask what it actually involves. Then it gets industrial very quickly. You need extraction hardware. You need energy. You need processing systems. You need purification. You need storage. You need maintenance. You need contamination control. And all of that has to work on another planet, inside dust, cold, communication delay, and long mission timelines. That is especially important because Mars soil is not clean or friendly in the normal human sense. Dust is already a constant problem for machinery and habitats. On top of that, Mars science has long discussed perchlorate-rich soils, which raise more questions about handling local materials safely. So even if the planet contains useful resources, those resources may be mixed into an environment that is chemically awkward, mechanically abrasive, and operationally expensive to process. Local materials are not waiting in convenient human-ready containers. They are embedded inside a system that still resists you. So use local resources is not a simple frontier message. It is really an industrial chemistry message. It means the crew may need to run machines that pull water from ice-bearing ground, process atmospheric carbon dioxide, store oxygen, possibly support fuel production, and do all of this reliably enough that the rest of the mission can depend on it. Mars turns survival into manufacturing. Not in a symbolic sense, in a literal one. If the systems do not produce what they are supposed to produce, the whole mission architecture can become much weaker. That is why the resource problem marks a real threshold in what Mars means. A mission that lands, stays briefly, and leaves is impressive. But a mission that makes oxygen on site, stores and reuses water, protects itself with local material, repairs its systems, and produces part of what it needs for long-term survival is operating at a much higher level. That is no longer just exploration by visitation. That is the beginning of partial independence from Earth. And that is the real reason Mars is harder. Not because the trip is longer in a simple way, but because the meaningful version of the mission is no longer about bringing enough supplies for a visit. It is about building enough local capability that the crew is not completely dependent on a supply line stretching across millions of kilometers. That is a much higher standard. It means your mission has to act less like a flight and more like the first version of an off-world operating system. So the resource problem changes the whole story once again. It tells you that Mars cannot be treated like a place where you arrive fully supported by Earth forever. At some point, if humans are going to work there seriously, the mission has to pull some of what it needs from the planet itself. Air has to be processed. Water has to be found or extracted. Materials may have to be used for shielding or support. Waste may have to become part of the internal cycle. Nothing about that is simple, but without it, Mars stays trapped in the most fragile version of exploration. The version where every survival margin depends on cargo that left Earth long ago. And once you see that, the final question becomes unavoidable. If Mars demands local production, long-duration survival, reliable return, autonomous crews, protection from radiation, and landing systems powerful enough to deliver all of it safely, then what is Mars really asking from us? Not just what kind of rocket, but what kind of civilization-level capability? Apollo already proved something enormous. It proved that humans could build a machine powerful enough, precise enough, and reliable enough to leave Earth, fly to another world, land there, and come back alive. That should never be talked about like it was a small first step. It was a huge achievement. Saturn V alone shows the scale of it. It could put about 125 tons into Earth orbit, or send about 50 tons toward lunar orbit. That is not just engineering, that is industrial power at a level that changed history. But Mars asks for something more than that. Not more of the same in a simple way, but another layer on top of it. That is the part people usually miss when they compare the Moon to Mars. Apollo proved courage, speed, focus, and the ability to execute a short extreme mission with very high precision. Mars still needs all of that, but it also needs endurance. And endurance changes the kind of system you have to build. A Mars mission is not just about getting the crew there. It is about keeping them alive and capable for years, with delayed communication, with radiation exposure, with limited maintenance options, with no quick rescue, and with a return path that may depend on systems sitting on another planet for a long time before they are used. So Mars demands much more than daring. It demands durable power systems, habitats that work as shelters and workshops, crews trained to operate with more independence, medical capability that stays useful far from Earth, software that stays reliable under stress, landing systems that can put heavy cargo down accurately, and probably local production of oxygen or fuel if the mission is going to be realistic at scale. That is a very different standard. It is not enough to be brave enough to leave Earth. You have to be organised enough to survive after the exciting part is over. And that is really the shift in the whole story. Apollo is a high-risk sprint. Mars is an endurance mission in the deepest sense. It is not just whether the rocket performs well on launch day. It is whether the whole architecture keeps performing after months of cruise, after landing, after surface operations, after long exposure to wear and isolation, and then still performs again when it is time to leave. That means Mars is not only a test of engineering power, it is a test of engineering maturity. This is also why the robots matter so much. They have been doing the hard groundwork, one mission at a time. Pathfinder helped show we could land and move on the surface. Spirit and Opportunity taught us how hard long-duration mobility and surface survival can be, and also how much more the machines could do than expected when they were designed well. Curiosity attacked the landing problem at a new scale and helped study radiation and habitability. Insight focused on the interior of the planet and the difficulty of operating fixed systems there. Perseverance added more autonomy, more advanced landing, and sample caching. Ingenuity showed that even flight on Mars was possible, but only by solving a very strange atmospheric problem. Taken together, those missions show something important. Humanity has not failed to go to Mars because it lacks ambition. Humanity has been slowly learning how many different impossible problems Mars combines into one destination. Landing was one problem, surface movement was another, power survival was another, radiation was another, autonomy was another, atmospheric behavior was another, resource use is another, sample return is another. Mars kept splitting into more and more technical battles the closer we looked at it. And that is the real answer to the question. Why is Mars so much harder? Because the Moon asked whether humans could reach another world. Mars asks whether humans can operate a fragile but functioning ecosystem across interplanetary time. It asks whether we can send large masses safely through deep space, land them through a thin and dangerous atmosphere, protect a crew from radiation, deal with communication delay, maintain systems far from Earth, use local resources and still return home safely. That is not a small increase in difficulty. That is a different category of mission. The Moon was a triumph of access. Mars is a test of sustainability. The Moon proved we could get there. Mars would prove we can keep going. The Moon proved that human beings could briefly leave their homeworld and touch another one. Mars would prove that we can build systems good enough to function between worlds, not just reach them once. That is why a successful Mars mission would mean so much more than just going farther. It would not only be a bigger distance record, It would show that human spaceflight had crossed into a new phase, not expedition in the old sense, but interplanetary operations, not just a heroic landing, but a durable chain of transport, survival, autonomy, maintenance, local production, and return. That is a much bigger claim about what kind of species we are becoming. Because once humans land on Mars and come back safely, the message is not only that we reached another planet, the message is that we learned how to keep a human system alive, across another planet's environment and the space between planets. That is why Mars matters so much. Not because it is the next trophy after the Moon, but because it forces us to answer a much harder question. Can human civilization extend its working systems beyond Earth and still hold together? That is what Mars really demands from us. Not just bigger rockets, though it needs those. Not just courage, though it needs that too. It demands reliability, patience, autonomy, industrial scale, biological protection, local adaptation, and years of disciplined operation. It demands that we stop thinking like short-term visitors and start thinking like a species learning how to function off Earth for real. And that is why Mars is so much harder than the Moon. The Moon proved we could touch another world. Mars would prove we can live through the journey, survive the environment, and work between worlds without falling apart. That is a much bigger threshold. And if we cross it, spacefaring will stop meaning occasional, heroic missions and start meaning something far more serious. This video is for educational or entertainment purposes only, and information provided in the video may be incorrect. If you enjoyed the video, consider subscribing to the channel and like the video.